Welcome everybody. Welcome to this event organized by EPMA. It's the first event of the year, so welcome. Um, yeah, I'll start by presenting you the speakers of today. Um, Unfortunately, I'm post-recording this because there was a problem with the recording of the original session, so I cannot let them speak now, but there will be Jose Salgado from the Canadian Chamber in Italy and three speakers from Space Commerce Matters in the United States, Cynthia Buteau, Molly Mulligan, and Jonathan Volk. They will speak later. Actually, we have quite a tight agenda, so I will go to show you what is the program today. I think you should see it on the screen now. Yes. So the first thing will be our short presentation about EPMA, especially for those who are not EPMA members, and also what are our views on what can be done in space for powder metallurgy. Then there will be, it's not in the agenda, a short introduction by Jose Salgado from the Canadian Chamber in Italy. And then the core presentation of today, which is given by Space Commerce Matters, as I said, about why on earth should EPMA care about low Earth orbit, LEO. I think that might be inspiring for you. If you haven't ever thought about this opportunity, you might have then the chance to discuss in a sort of brainstorming at the end, and the questions and the answers time. Maybe we'll have 20 minutes or maybe a little bit less, but we will probably extend also a little bit in the afternoon. So again, thanks for being here. And as the time is tight for you, I will go straight to the presentation. So EPMA first. I give it also on behalf of my colleague Kenan Boz, who is in the background, but it's easier that I only speak today. So European Powder Metallurgy, 30 years old, 32 years old actually now. We are a non-profit association that wants to promote and develop PM technology in Europe and develop its future, and also represent the European PM community at any level it's needed. And we're made of members. Members are the rulers in EPMA, and they decide what we have to do. So members, you can see the distribution of members here among the supply chain on the left, mainly parts manufacturers, but also raw materials, also equipment manufacturers, also research people, and so on. In terms of geographical area, you can see mostly from Europe, of course, 1/4 from Germany, but also from outside, from Asia, from America, from United States, from China, from India. We have a lot of members also overseas. It is possible. So it's a wider sample of the PM community, actually. We cover the supply chain, as I said, starting from the metal powders and their consolidation into shapes and parts, and the use of these parts and components. And also all the equipment manufacturing for all these sectors, and also the research devoted to this sector all over Europe, and as I've seen also outside of Europe a little bit. We have this pictorial view in EPMA of powder metallurgy as a tree. The tree is growing from the powders, ferrous or non-ferrous, and developing branches, which are all the technologies that have been developed over the years to produce these parts from powders, and also materials. And so every time we see there are new processes, new materials that are developing, and they have needs in terms of fostering projects, of being represented, of having the chance to network within themselves. Then we develop new sectors, and what we do, we create a sectoral group. Sectoral groups are listed on the left. There are 6 of them. They meet, they organize surveys among the industry. They organize seminars or webinars like the one we are in. We have publications on technologies, on the case studies for end users, for instance, and we foster research and innovation in each sector. And we do it by creating events, for instance. We have a full calendar for 2021. I can show you later. Our most important event in the year is the European Congress and Exhibition, and it will be virtual again this year, like last year. We organize, as I said, seminars and webinars. You can go to the website and find all the details. We also have specific websites dealing with specific topics, like, for instance, for designers, like the Design for PM or the Global Property Database, and also training. PM Life is one of these. As I mentioned, the booklets, here are the examples of the Spotlight on PM with the black color on the side, and the colored ones in the middle are the introduction to booklets. The Spotlight on PM are basically for end users to understand exactly what PM is capable of. And then we work on social networks to advertise, to promote the technology, LinkedIn, Twitter, and also we have a YouTube channel with many videos you can watch. I was mentioning the events calendar. This is not exhaustive, but you can take a note of all these events that will happen in the next months and this year. But the biggest event is the Congress. We were hoping again, trying to go to Lisbon for, as you see on the bottom right, for this year, after having attempted last year, but we have decided to go virtual again. And we already collected the abstracts for the virtual Congress, but there will be also a virtual exhibition this year. So it will be hopefully a big event, but even bigger should be hopefully in person next year, the World Congress in Lyon in France. We hope really to gather many people there and start again having a real Congress like normal. Finally, about what we talk when we talk about representing the PM community, we normally liaise with other associations because the topics we're working on are bigger than us, bigger than just powder metallurgy. And so, for instance, for ISO standards or the chemicals issues, we normally work together with other associations and to make our voice more listened. Finally, the research, and we come closer to the topic of today. Research, we normally carry out research in European projects, like the names you see here. We can mention the last two, Supreme, which just ended last year in December. Well, so just less than 1 month ago, and SAM, which is going to be there until 2022. We normally work in the dissemination of results and organizing events or designing and producing graphic content for websites and newsletters and so on. But one thing that could be used for the topic we're discussing today is what we call the club projects. It's a tool that we have developed for our members. Normally, a small group of companies, 5 to 10, they join and share the cost for a small item of research that is carried out by a contractor. Duration typical 1 year, and size is 30,000 euro normally. We had already about 30 of them, and they're very popular, and they were fine. So this could be also a frame to use for the topic we're discussing today, as I said. So my last slide is about why this webinar. And actually we start from the fact that we have been asked if we could try and organize participation from European PM community in a low Earth orbit flight for research experiments. And there have been experiences of such studies already carried out on the microgravity aboard the ISS. And I remember this study on the sintering or heavy tungsten alloys. But in general, I don't know if you have any ideas already on doing this, but there are probably a couple of different things that can be done in low Earth orbit. One is bringing powder metallurgy processes in space. So, for instance, if you think of using, I don't know, additive manufacturing in space, think about how to have a powder bed, for instance. You cannot probably have a powder bed because the powders are just floating around. And yeah, but on the other hand, maybe vacuum is a free thing in space. So there are pros and cons for doing that. So we might think about something in this direction, or the other direction, on the other hand, which is probably the one mostly used by other companies in the past, is studying the processes under low gravity, under microgravity. So basically almost without gravity, to see how they work without gravity and understand them better and improve them also on Earth. That's the other direction. There might be other ideas, but this is what I've guessed on my side. And how to do this will be explained later by Space Commons Matters and the Canadian Chamber, maybe also in the next weeks. We expect that the financial effort will be much bigger than the normal club projects. So this can only be a joint effort, really, with many members sharing the cost. Surprise me. But I think it would be just a very large club project that we are ready to help build and manage, as we normally do with club projects. We are requiring that the participants will be EPMA members, of course, but that's more or less it. And finally, the time frame. I understand the flight is not going to be this year, but still we need to have some information about the time frame that we have to imagine something. So finally, feel free to pose all questions to us, to SCM, to the Canadian Chamber, and try and understand exactly what can be done. I think this is what I wanted to tell you. If you are an EPMA member, you already know where to find us. Otherwise, please take note of our emails at least and contact us, and of course contact SCM, and feel free to pose us any questions in the Q&A afterwards. And now, as I said, I will just stop sharing my presentation here and give the floor to Jose Salgado, who is going to talk us a little bit with some slides. I understand. Jose, the floor is yours.
Possible that can happen inside this vessel that is going to go into space. So we know what's going to happen up there. We know what we can do up there. But now the interesting challenge, and this is the opportunity for everybody, is to link how those applications can link to actual solving problems here on Earth with your industry. So at the end of this conversation, after my colleague Jonathan runs the presentation, we're going to give a lot of time to have a brainstorming session. We really want to hear your questions. We really want to hear your proposals. In many aspects, this is new to everybody, so we dare to dream for those who are dreamers, but also we dare to actually do very hard science with results that impact the balance sheet, because that's the other thing we propose. This is not just a matter of flying something for the sake of flying, but it has to be an economical and financial reason, and we are able also to help you further with that. So at the end, you'll find our contact details, so we will ask you to submit any questions, any comments that today we could not address. And that's it for me. Just want to invite you to keep an open mind, to keep thinking about the problems and challenges and opportunities of your industry, because you are the experts. And let's see how we can link and create ground-searching research, experiments, and manufacturing that it has never been done in our lifetime. So I'm going to leave you with a very exciting video of how this vessel look like and some of the capabilities. And after that, I'll just pass on the word to my colleague, Jonathan. Thank you very much.
All right, start the video.
Well, I think it has no sound, so I'll just take some time to see how you see there you go. It comes inside the rocket, and that is called a Space Rider. Inside it has many lockers for different kind of experiments. And look how nice it looks orbiting our planet. And it also has a hatch that opens. So if there's an experiment that needs to have the direct effects of low orbit, it also can be possible. It can also turn, and this is also for remote sensing, as you can see there. So it's very flexible. Also from sideways for deployment of satellites if needed, or some other kind of application. And then it gets ready to re-entry. And again, the time, it can be up to a few months. So it also, every mission can change depending on the different types of requirements. And we will get you more details about this. And there it is, going back to Earth. And landing safely. So assuring all the experiments come back in a safely manner. There you go. It sounds easy, but there's a lot of technology behind it. But I wanted to give you an idea of what any potential experiment that you are interested in flying would look like. And that's it. Thank you very much.
Thanks, Jose. Jonathan, can you go to the next slide? And thank you to Bruno for a great introduction. And Bruno, for somebody that has not worked in the space sector, I was very impressed with your knowledge and the ideas that you've already identified as being potential topics. So great job there, Bruno. And we're really looking forward to continuing discussing some of those ideas that Bruno raised at the beginning. My name is Cindy Buteau, and I am president of Space Commerce Matters. And along with Jonathan and Molly, our background is working with the International Space Station National Lab. I actually helped stand up the organization back in 2011, the organization that manages the National Lab. And we were faced with the big challenge of reaching out to new to space commercial users and creating value or propositions of why would you do anything in space? Because, really, as all of the space agencies right now are looking at moving more into the moon, Mars, and beyond, the exploration agenda, they're really looking at low Earth orbit to become a viable and scalable new marketplace. And that's the way that we're looking at it now. What are the types of things that are taking place in low Earth orbit? Formulation of novel materials and better manufacturing processes. We've done a lot on sustainability programs using all of the phenomena of low Earth orbit to look at plastics in the ocean or sustainable crop production, energy conservation. Jose mentioned, and I think Bruno mentioned, drug delivery systems. Many pharmaceutical companies are looking at discovering and delivering new drugs. And we're going to go through this presentation and give you case studies of some of these examples. We're looking at aging and chronic disease and regenerative medicine. What happens when we are able to produce new organs in low Earth orbit and bring them back down for better organ transplant procedures? We mentioned crop science, indoor and vertical agriculture, all of the challenges we're facing globally with very tough crop growing environments right now. And then we also talk about remote sensing and the satellite technology. I think that's what we're all more familiar with, but there's many other things happening from a microgravity and an accelerated degradation perspective. Next slide, Jonathan. And so technically, why space? The reason we go into low Earth orbit to do research, development, or manufacturing is based on these three primary conditions. The first one is microgravity. And Jonathan is going to take us through many of the phenomena. What happens when you remove that lens of gravity, and what can you do and discover from a research perspective or a manufacturing perspective? Jose pointed out the external platform related to Space Rider. What actually takes years or decades to degrade here on Earth could take weeks or months in low Earth orbit, and that's because of the extreme harsh conditions. The heat and cold cycling, the atomic oxygen, the radiation, the debris impact. Again, those are very harsh conditions that cause or result in greatly accelerated degradation testing of materials. And then we've mentioned the vantage point, all of the Earth observation that you can do from that vantage point of low Earth orbit. Next slide. And again, we talk about this in more detail, and it's really the basis of the propositions that we're going to discuss with you today. It's these three big areas that are providing the opportunity that both Bruno and Jose discussed. Next slide. And so when we talk about the research and the industries, we specifically talked and targeted this presentation on the areas that we believe most relevant to you, but the material science, chemistry, fluid dynamics, and et cetera, really impacting a broad variety of industries. And when we talk about the activity that's taking place in those industries, we're not talking about, supporting exploration or spaceflight. We're talking about conducting research or manufacturing that would benefit these industries and those processes back here on Earth. And that's really the point of today's discussion, is translating why space to how it could impact your activities back here terrestrially. Next slide. Over to you, Jonathan.
Okay, thanks, Cindy. I'm Jonathan Volk. I'm the Director of Commercialization Strategies at Space Commerce Matters. I'm going to give you a quick overview of some of the high-level science benefits of LEO, especially related to the research areas that you guys care about as powder metallurgists and related areas. So scientific behavior in space, it really comes down to the fact that, as Cindy mentioned earlier, microgravity suppresses these forces that are very common on the ground: convection, buoyancy, and sedimentation. And when those are suppressed, other forces dominate, and they allow you to really uncover more of a total picture of a behavior of a system. You can't really isolate those forces on the ground because these three forces here really kind of get in the way. So it's a great way to really unmask your system, your process, whatever it may be, to get a full understanding of how it behaves. So the first example is material synthesis. So again, and all these examples, it really comes back to the suppression of those gravitational forces, convection, buoyancy, and sedimentation. So you can synthesize more ordered materials in microgravity, even on a molecular level. You can get more uniform crystal growth. Polymers can form more orderly. There's materials that are produced with fewer defects because you don't have those forces, convection, buoyancy, and sedimentation, that a lot of times cause those the defects in material synthesis. And this is the case across all types of materials, whether you're forming a polymer, a metal, a semiconductor. It's really a great way, microgravity, to study and eventually formulate materials with fewer defects. We're going to talk about some specific case studies of those here in a little bit. It's also a great environment to look at material behavior and from like phase transitioning, measuring thermophysical properties, because those gravitational forces are suppressed. You can evaluate coefficients for modeling much better, study phase transitions where surface forces dominate, etc. So it's a great way to really evaluate a material system, get material properties, and study their behavior. From a fluid dynamic standpoint, as you would expect, with those gravitational forces suppressed, other forces dominate a fluidic system, such as diffusion, surface tension. You can study interfacial behavior much more easy because it's a surface dominant environment. So a lot of fluid studies and transport studies have been done over the years in LEO and utilizing the benefits of microgravity. Reaction chemistry, we're also seeing some growth in that area, especially on the mixing side. We'll get to some examples here in a little bit. There's also combustion studies that have been done, because in microgravity, the combustion mechanism, it's a diffusive flame, or sorry, it's a diffusive flame and driven by conduction as opposed to a convective flame. So several combustion studies have been done, and also corrosion, utilizing that atomic oxygen in high concentrations in space. Space is a very rapidly corrosive environment, so you can look at material degradation, as we mentioned a couple times earlier, much faster. So that's just a very high level of things, and we want to now go into some specific examples of flight projects that have been flown in LEO or on the International Space Station. And these are, again, mostly relevant to your area. There's some that are very relevant, but we'll go through some of these. And these are projects that have already been flown, are currently in space, or about to fly very soon.
And Jonathan, let me just add, Jose at the beginning mentioned the work that we've been doing related to applications, like what are the relevant applications and what are the relevant markets for Space Rider and, in this new space LEO economy. So, the work of Jose with the Canadian Chamber in Italy, really understanding that new space dimension and that market dimension, along with these examples from what's already been done primarily on the International Space Station. What we're going to ultimately get to in the brainstorming are what are those most relevant applications that could benefit your industry. So if you just go to the next slide, Jonathan, again, what we've done here is we've given you the example of the case study. With the first bullet points, you're going to see, what was the science behind it. But ultimately, in all of these case studies, what we've tried to do is give you what's the ultimate outcome? What's the ultimate impact of actually doing something? Because if it's not going to be beneficial from a business standpoint, why would you do it? Businesses don't operate because they want to do something that's interesting. There needs to be a real value and an impact. And what we have shown through the work on the International Space Station is we actually can calculate value and impact. We looked at the range of projects that had been done on the space station, and we could say that the incremental revenue associated with it was about $1 billion. We were looking at total addressable markets of about $160 billion, and things like accelerated time to market and new solution pathways. There were so many different types of outcomes associated with it. So as we continue to talk about what these projects could look like, and when you need to go to your chief finance officer and talk about why you would do something in space, we have a lot of this data of what that ultimate impact is. So Jonathan, why don't you go ahead and zoom us through these case studies?
Okay. There's a fair number here. I'll just actually touch on a few of them in the interest of time. So again, we'll send these slides out when we're done so you can have all these, but I'll just touch on the few that are probably most relevant. One is involves retinal implant manufacturing. A company called Lam Division did a R&D study in microgravity. They utilize electrodeposition, which I think is a method that powder metallurgists use in their processing to formulate retinal implants. It's a layer by layer process to make a layered material. And being able to do this in microgravity, they're able to show that they can make these retinal implants with much fewer defects and hence a better performing retinal implant. And that can be very important to make, obviously, to make significant impact in treating macular degeneration and other eye diseases, really reducing, improving the sight of a lot of people who couldn't otherwise see. So they've actually done a proof of concept experiment. They're going to be doing a future scale up in microgravity to actually produce these. So that's kind of the trajectory that we'd like to see, where Leo is not just an R&D platform, but also can be a pathway to manufacturing as well. And this is an example of that. More on the fundamental side, we have an academic industry partnership. Penn State University here in the US and BASF partnered to really look at how concrete mixes in microgravity. What happens when you don't have that those gravitational forces? Does it mix more effectively? Does it produce a stronger product? Can that be used to formulate more uniform concrete on the ground, or the stronger performing concrete, and also reduce things like reduce carbon dioxide emissions while during production, things like that. So a very simple study, but they can learn a lot about by eliminating those gravitational forces and get a better understanding of the complete picture. Another one, NEMAC, I don't know if you've heard of this company. They're a global company that manufactures metal alloy castings for the large automobile manufacturers. They have an issue in their manufacturing called hot tearing. So when the alloy solidifies, they get tears in it and basically have to scrap the part. And they think that there's more to it than just the gravitational forces that cause the cracking. So they want to remove that and really get a complete understanding of what causes that hot tearing that they can't see on the ground, so that knowledge can help them improve their casting processes, that solidification processes on the ground, so they can make a stronger cast that's less likely to crack. And that's obviously beneficial for them and their customers because they don't have to scrap as many parts.
And Jonathan, that's an example. Bruno mentioned what are the common challenges that that many different organizations face across industries. This is one of those examples where it would impact automobile manufacturers, aircraft engines, anything related to producing a thinner, better performing alloy. So these are one of the examples where if you were to look at these common, maybe non-competitive type of challenges, this hot tearing area is probably a very good candidate for that.
Okay. Goodyear tires, another example. They want to make see if they can formulate a more stronger, a more optimal silica polymer structure to make that can be used to make the rubber, which then goes into more fuel efficient tires eventually. Because if you have a higher quality silica, a better performing rubber, better performing tire, that can lead to increased fuel efficiency in cars, reduced pollution, better tire traction, increased safety. So that's a major, obviously, a well-known brand that's utilizing the R&D or the microgravity environment for R&D to help them formulate a better product.
And why don't you go to Delta Faucet? I just want to give this example where we visited Delta Faucet because they were right across the street from Eli Lilly, a large pharmaceutical company based in Indianapolis. And they wanted to be the manufacturer of sinks and toilets for the International Space Station. But ultimately, when we walked out of the meeting with them, we had a long list of projects that could actually benefit their operations here on Earth. So for many of you that are sitting out there and saying, well, I don't really know how this could impact me, it really is about looking at these case studies, we'll look at what has been done and then understanding. And in this case, we looked at microgravity's effect on droplet formation so that they could create a shower head that you would feel wetter with less water. So a more water conservation friendly type of shower head. And also it was a very big seller, a big part of their marketing branding effort, even though it was a true research and development type project. Go ahead, Jonathan.
Okay. This one was actually a series of experiments done by Procter & Gamble. They wanted to look at the shelf life of their products to study the stability of colloids. They have an issue, obviously, their products, the shelf life has an issue. Phase separation is a big contributor of that. So you get the phases in the product, one sediments out over time, and the product is no longer effective. But similar to some other examples we talked about, it's not just sedimentation that causes phase separation, but on the ground, sedimentation is what drives it. So they want to really uncover, see the whole picture of what causes phase separation, so to isolate those non-gravitational contributions. So they've actually done a series of experiments over many years, and they've actually gotten a few patents from the results they've done in space. So they've taken that knowledge and applied it, obviously, for patents, but also to improve the shelf life of their products. So that's a kind of a repeat user that's used the microgravity environment over several years. So they're obviously a great example. In general, we talked about retinal implants using in-space manufacturing. Another example is optical fibers, Z-bland fibers. There's actually current test cases and initial pilot manufacturing utilizing tools in microgravity to make these Z-bland fibers, because you can spin these in microgravity with fewer defects, and hence they have much better conductivity properties, etc. So in general, we're really trying to, as I mentioned earlier, trying to use a low Earth orbit as not just a platform for R&D, but also a trajectory to actually manufacture things in space, because you can make them so much more superior to anything you could on the ground, because you're really reducing the defects that can be the defects can be reduced by formulating in microgravity, because those gravitational forces are suppressed. I'm going to skip through a couple here in the interest of time. So the last example I'll show is obviously something that Bruno mentioned earlier. There's a study done recently by San Diego State University looking at distortion and sintering. So again, kind of the same mindset. What non-gravitational forces drive component densification during liquid phase sintering? So again, it helps you get that total picture of what's the full story behind the process. What are the issues? What are non-gravitational issues that cause this, but you can't study them on the ground, so you go to space to isolate them. And this can obviously have impact in understanding more about the sintering process for use in space, because it has a lot of applications, but also taking the knowledge and applying it back on the ground for ground-based sintering processes. So with that, I'm actually going to touch real quick, and I promised Bruno and I did not coordinate this ahead of time, but I'm just going to share what we thought were some possible flight concept areas, and Bruno actually touched on them. So I'm just going to share a few examples here to just kind of maybe get the brainstorming going. So looking at microgravity, how does it affect some of these production methods of metal powders? Obviously, I mentioned electrodeposition with the retinal implant case, but there's obviously a lot of production methods that powder metallurgists care about, including these here. So how can you, again, isolate the non-gravitational forces that contribute to these processing? Can you study them and maybe eventually learn how to use that to your benefit to potentially take these processes for actual manufacturing in LEO, because it could be done more superiorly with the elimination of those gravitational forces. Also looking at mixing, that concrete example I talked about, the powder particles, how do they mix with lubricants without density gradients? Looking at the furnace, the sintering using a furnace without convection, could you weld particles more evenly? A couple other cases looking at post-sintering processes. There's a lot here, so looking at how what happens when you have a surface force dominant environment, how does that affect these types of processes? We're already working on with CVD has been studied before in microgravity. It's an area that's looking to be expanded capability going forward. So that's one of the post-sintering process areas that could be interesting along with these others. And also looking at non-conventional powder metallurgy processes. And the one that Bruno did point out, additive manufacturing. There is additive manufacturing capabilities on ISS in space, utilizing a lot of different additive manufacturing techniques, filament printing, and other types of like bioprinting, etc. But looking at taking your additive manufacturing techniques that you utilize for powder metallurgy on the ground and see, can you make those more effectively in space, or make them in space for use in space, because there's obviously a lot of space applications for this type of product as well. And lastly, looking at utilizing the external conditions of space to test your metal powders, your manufactured products. How do they degrade much more rapidly in space than on the ground for both space and Earth-based applications, taking into effect all those unique phenomena of space, the thermal cycling, the atomic oxygen, the debris, the radiation, etc. So it's a great way to test for degradation and failure mechanisms. So before we get into the Q&A, just want to quickly point out, I know you guys are probably thinking about all these great ideas you could do, and I'm sure some of you might be jumping one step ahead. How do we get there in space? How do we get up to space? Well, don't worry about that for now. We just want to tell you that there's a lot of service provider support that should you want to take something forward, we can work with you on really designing an experiment or a platform, a payload that can really make it to LEO and get the results that you want to get from your research. So we just want to calm anyone's concerns ahead of time. We can work with you on that going forward. So we will get into the Q&A, and actually I just want to share the last slide here. And again, we'll send this out. So the main contact points for us, in addition to Bruno for this, if you want to discuss farther, is Jose at the Canadian Chamber in Italy. His email address is here, and myself at Space Commerce Matters. So again, we'll send these slides out. You'll have our email addresses if you want to talk more to us about that. But hopefully this Q&A session we're going to have here and the brainstorming will get you guys kind of thinking about, hey, what can we do in space that's relevant to our industry, our organization. So with that, let's go back to Q&A.
Jonathan and Bruno, do you think it would be helpful to go back to your list, Jonathan, just to be looking at it, the list of concepts, just to have that on the screen?
Sure, I can start with that.
Yeah.
So I don't know, Bruno, if you want to open it up to questions or how you want to handle it, or
yeah,
you take it from here.
First of all, thank you all for your contribution. I think we can try to have some question and answers now. Yeah, I don't see raised hands, so I'm trying to stimulate some discussion. Thanks for giving also some ideas on what can be done, and we've seen the case studies. I think maybe many people in the audience are really thinking not only how do we get there, but how much will it cost to bring an experiment to space. That will be probably one of the key points today, because maybe they have not already thought about doing that. Maybe just because they think it's outside possibilities, you know. So we need to probably help them understand. Don't know who can comment on this.
Yes, I can say something about that. I think we already have somebody, but yeah, maybe the ideas will not come today immediately. And in terms of price, well, space and these applications are based on the complexity of what you want to do. So we cannot really provide, you know, and again, this device, vehicle, is being built as we speak. So the launching date, I think we never mentioned this, was 2023. So far, it's the launching date. So we have this window of opportunity from now to then to identify and go into more detail about the cost. But it really depends on the application.
Right. I think we have a couple of questions actually in the chat, so I would ask Peter Quoteback to maybe open the microphone and pose the question himself.
Yeah, thank you. The question is, the one question is what do we have to calculate for the launch? But the other question, and which is much more important for us, is what are the costs for the organization of the bureaucracy in terms of product assurance? Do you have any halfway reliable numbers on your efforts and how to organize that?
Can I just ask for clarification? Are you asking for, when you talk about product assurance, are you talking about the quality of the project that's flying, or how are you, could you just clarify that?
I mean, if you want to supply your parts for the flight, most of us will supply parts and don't do experiments ourselves, but we will supply parts. And the question behind is what we have to do in order to ensure that the part in order to ensure the quality. So they're quite high efforts. I know some ideas behind about the associated product assurance, but the question is in how far you maybe have some numbers on that.
Yeah, and I would just say, and getting back to Jose's point, we don't have exact numbers now. The other point I would say is it's very difficult to sort of think about these processes, because what you do or how you conduct an activity on the ground is not going to be how it's conducted in space. And there's a whole translation process that takes place once you have the concept. So say you're looking at a mixing process or a crystallization using furnace, looking at these particles, uniform particles for welding. What you're doing first is identifying what is your challenge, what's your pain point here on Earth, and what are you trying to achieve from an outcome.
Did we lose Cindy?
Sorry?
No, we didn't. We can hear you, Cindy.
We can hear.
Okay. And so what happens is we identify the concepts first, and there's a whole translation process. That's the whole integration of taking something that is typically done on the ground to then doing it in space. And that, there's a role of the service provider, there's the role of us that actually are there to do that translation for you. So I would not worry about that right now. I think what we're trying to understand are, what are the biggest problems and challenges you have in the PM area in general? And where would it make sense to use low Earth orbit to solve some of those? And then what we can do from there are take these project concepts and really bring them down into what would this look like tangibly? What would the timeline be? What would be the requirements on your part? What would the cost? Those types of things. But in whenever we're talking about bringing something to low Earth orbit, we do not start with the facilities or capability. We start with what is the concept? What is technically you're trying to achieve, and what are those outcomes? And then we can move more to that type of discussion. So I don't think it answered your exact question, but hopefully it gave you a sense that doing something in space is like a translation.
Okay, thank you. Thank you so much.
You're welcome.
There was a question from Hank van der Berg where they had to leave, and I think it was more or less on the same line. So maybe we can move to Kauzik, who has the raised hand, so he might speak if he opens his microphone. Yes.
Hi, thank you for the presentation. I have heard about these experiments in space and microgravity earlier, but my question is about the scale of it. What could be the scale of a typical experiment in microgravity condition? For example, if I want to do is liquid phase sintering, which is very interesting to do without the gravity. Can you hear me?
Yes.
Okay. So in case if you want to do a microgravity sintering, I would also need to have a certain atmosphere for sintering. So we need to have the gases which we need for the sintering atmosphere, and what could be the maximum size of the furnace which we can take, and these are, I think there should be some limitation with that, with the size of the furnace and then the other requirements for the experiment.
Yeah, I mean, that's a great question. It's a great point. And size is definitely an issue. Smaller is better. Volume, lower volume is better. You know, weight, the lower the better. All of that sort of stuff does matter. So the real art of this is to, again, it's in that translation. What's the outcome you're looking to achieve? And, you know, how do you achieve that sintering outcome without flying a furnace that you would usually use terrestrially? And, you know, I hate to continue to just say the same thing, but you're not going to use the same hardware or capability that you use on the ground that you use in space. And that is the art of how we translate it. So once we understand that you've got a desire to look at a sintering process and what your actual outcomes or objectives are with that, we will then translate into what would be the appropriate hardware, what would be your maximum size that you could use as part of this this experiment, and we would come back, and it's a real interactive process to define what that space-based project would look like to ultimately, and this is the most important part, to achieve the objectives that you're looking for. So that really is, you know, and all of the case studies that we went through earlier are talking about those outcomes related to a project that the organizations didn't envision at the beginning. They had their objectives, what they wanted to achieve, and then, you know, it was a whole retrofit into how do you actually do it in low Earth orbit. So again, I don't think I'm answering directly your question, but you know, there is a way to achieve your objectives with the space-based hardware, but it's not going to look exactly like it does on the ground.
Yeah, and I'll just add real quick, Cindy. I mean, obviously mass and volume are kind of limitations, but in terms of temperature control, pressure control, those really aren't. So for the most part, you should be able to operate a procedure at a certain temperature that you could on the ground with a certain pressure. So that those aren't as constraining as obviously mass and volume are. I know you mentioned pressure earlier, so that's.
Yep, great.
I guess vacuum is almost inexpensive there. You don't need any pump, so you can spare that.
I think you could also add to your title, Bruno, marketing executive here.
Oh,
like
sorry.
I liked your earlier line that vacuum is free.
Yeah, that's free. Yes. There's Stephen Mosley, I think, who has a question. Stephen.
Yeah, I mean, I know there's been a lot of work on microgravity, particularly the sintering, the liquid phase sintering, the synthesis of powders and so on that are related to hard materials and heavy metals, refractory metals. I was actually just thinking generally from the space agency viewpoint. I mean, AM for future missions, Mars, so Moon, Mars, and whatever is been discussed for decades. Do they have any topics where we could help them, just sort of thinking differently, rather than us having to come up with our own projects where, yeah, maybe it's a nice academic. I mean, I'm coming from industry now. Maybe it's a nice academic thing, but you know, where we could physically help what is already being planned or unknown. You know.
I don't know if there's anyone in the audience also able to comment on this.
Yeah, I mean, we're a small association, and we're not, you know, we're not experts on space and microgravity.
Exactly. Yeah, exactly.
Can I ask a question, Bruno, at this moment?
Yeah.
Or actually to Cynthia. Hi, by the way, I'm Ken Ambos, colleague of Bruno. Did you have any interaction with MPIF, the American Metal Powders Industries Federation? They might have some knowledge about what's going on with low orbit works with powder metallurgy.
I think we have also some friends here from US at the moment, but yeah.
I mean, Ron German in San Diego and former Penn State has been working on this, and there are people in Europe, in Belgium, Leuven, that have worked on it in institutes in Italy as well, on microgravity experiments, but more on the sort of academic side, I think.
Yeah.
Yeah, and I think, you know, we have seen a lot of that. You know, when we first knocked on the doors of commercial organizations in 2011, they were not interested because they didn't think space was relevant for them. And a lot of the first investigations in low Earth orbit were done by universities and academics. And then we saw many different partnerships. You know, Jonathan mentioned the Penn State BASF partnership, looking at cement mixing. And then we saw many different commercial companies just doing work on their own. So I think there's a lot of different models. And, you know, Bruno, the way that you described the support that your association gives these companies in conducting these types of projects, you know, I think that's also a really good model to think about, especially related to those common problems that everybody faces as they're going through their PM activities.
Yeah, that's a possibility that we offer. Any other questions from the audience?
Bruno, can I ask the audience a question?
Yeah, sure.
I was going to say, out of the business or the case studies that Jonathan went through, and also the ideas that both Bruno and Jonathan mentioned in terms of the different areas, did anything sort of stick out more prominently than others? Like, we've had a question on sintering, but are there other areas that you all face that you could envision that could be impacted by the phenomena of low Earth orbit?
It's a good question. While they think about that, there is someone wanting to give an answer to Stephen Mosley to the previous question about the space agencies.
Yes. Can you hear me?
Yes, we hear you. Advenit.
Yes, I'm Advenit Makaya from the European Space Agency. So I think that question is quite appropriate for us. Yes, there are things that we are interested in from manufacturing in space point of view. There is more and more activities now about in-space manufacturing. So not only looking at terrestrial industrial processes and the effect of microgravity, but really manufacturing parts in space, either for astronauts during long exploration mission, or manufacturing satellite parts, like very long solar arrays, for example, or very large antenna, which you could not launch from Earth because they would not fit in a rocket. So for that, we need to develop manufacturing processes. Additive manufacturing is an example, but there are others which would work in low Earth orbit or later on the moon or on Mars. So any study, experiment which would progress the development of in-space manufacturing technologies are of interest to us. And I'm going to make selfishly a little bit of advertisement for a workshop that we have on in-space manufacturing in the beginning of March. And you are welcome to contact me to get more details on that.
No, absolutely. Thank you, because that's, I mean, industrially, we're sort of more used to tackling a problem rather than trying to invent something new, to actually try and address something that's already clearly in front of us. So yeah, I think that would be interesting. To answer the question to the audience about what stood out, I mean, to me, it's certainly the powder and the hard materials. We talk about additive manufacturing, but there's going to be subtractive manufacturing. You're going to need machining. It was already mentioned, it's not just one in-space manufacturing technique that will be used. And the synthesis of hard materials or ultra-hard materials, whether it's PVD, CVD, the diamond or hard refractory carbide materials in situ, would be very, very interesting, I think.
Great.
With Advenit, if you want to post a link for your workshop in the chat, you're free to do it.
Okay, I'll do that. Thanks.
Might be useful for everyone. So, any other comments on the question from SCM. Sorry, I have SMCs in my mind because they are soft magnetic composites that we work on. So I get confused.
Yeah, functional materials and magnetic domains and what happens in.
Oh, yeah. Why not? Yeah. That's also a possible topic. Yes, yes. But in this case, it's just confusion on my side.
And I might add something at this point,
sure.
Because, and I understand the desire of having a number to begin with to give you an idea, and this is something we internally also discuss a lot. So I think the safest thing we can say so far is that it starts at the 6 figures. Anything we want to do in that regard, that would be the starting point. Yeah, I don't know if that helps on a little, but it's as much as we can do talking about the abstract, right?
Right. That's what I mentioned. Would be a very large project in our terms, because they normally think about things in 5 figures. So we have the link to the ESA workshop as well. Thank you. Yeah. Any more comments? Questions?
Well, I just also want to add, given that there's no comments or question at this moment, I think space, we start to hear more and more about applications that, and I think the case is not something that will immediately might come right now in a conversation like this, and we are aware of that. So what I just want to say to the listeners right now is that if this conversation has some impact, maybe not now, but maybe in the future, we're also interested in continue the conversation about it. So if you want to contact us through the association or directly to us, we're all going to keep each other in the loop. We want to hear more about, because it's also sometimes not easy about, like, maybe right now in front of everybody proposing an idea that might not sound relevant, but we want to explore those ideas too, maybe in a different, in a private setting or one-on-one. So I understand that it's not easy that people come with ideas right away or brainstorming. It's naturally not happening, especially with something so new. But I think just in your daily life, you're going to keep hearing about a space. And we can tell you from our experience that this vehicle is a real opportunity. Right now, the fact that we are able to do experiments and manufacturing and have it back with a short window of time and having all the effects of lower orbit, it's really relevant for those companies who are also interested in going Moon and Mars, because we need to test those materials. We need to test those effects. The same effects we like, even when they're talking about agencies, although we're not an agency, they need to have certain processes and certain certifications. And let's say that this could be one step forward if there's also a company interested in manufacturing in situ in space. This is a good stepping stone for that. And that's it. That's pretty much all I want to share. Yeah. Keep us in mind.
Yeah, Jose, I think you just brought up a really good point that I don't think we really stressed, which is, going to the International Space Station is not easy. And what's even more difficult is bringing things back from the ISS. So this vehicle having both up mass and down mass, being able to bring something up, potentially manufacture it, or, at least having your item to return to you in a period of time within, weeks is really a breakthrough. And having worked with so many organizations going to the ISS, it's very, very difficult getting things back. So this is something that is really exciting about Space Rider.
And I also like actually what was it? Stephen comment about, like, the industry is more about solving problems and I like that you have that point of view. And yes, we can also use your client's problems, but now you have another option, which is a space. So let's just put it like that. Among all the tools you have for solving the problems of your potential clients, now you can add a space into that mix. So I think it's interesting too.
Yeah, certainly exciting. Thank you.
Can we say something about the time frame? So you mentioned that the flight would be not this year. When we should have sort of commitment if we want to start building something for that flight? Is there a deadline, more or less, in the next months, so that people know how fast they have to think?
Well, I mean, still going to space is a long process because we need a lot of certifications. That is the reality. But I think one of the first steps we need to have for us to actually go down to a price, to exact number of how much it would cost, it's some kind of interest from the companies. So that can come as sooner as within the next month or the next 2 months. And then that doesn't mean that you're ready to fly. That means that then we will actually look. We know there's an interest. We know there's a potential application that can have a direct impact with your industry. And then we look into it. That's what it really means. So I think it's important also to take advantage of that opportunity that at this moment, as we speak, might not require a huge or even any financial commitment, but it will allow us to know exactly to set the guide of where to look at, So those are the time frames we're looking at. Now, once we have the interest, now we have an idea of what we're dealing with, then we will look into the price with more detail.
Yeah, and I would just add to that, that translation process of how you do it on the ground to how you do it in space is really what takes that time. So if we could identify project concepts that are most interesting and really have the ability to work into what would that really, what would that look like, especially related to this maiden flight, which is a real opportunity. So I think it's going to be an opportunity in terms of being, in on the ground floor as well as financially. So I think, to what Jose just said, if we could have sort of a working process on coming into some real concrete ideas over the next month, I think that would be really helpful in at least getting into a queue for that potential maiden flight, which I think could be very interesting for your members.
Okay. So we are, of course, available to collect interest. You can also talk directly to Jose, to SCM for details if you want more details, I think. But we're available. And yeah, if there are other comments, we can take that. Questions, comments. Otherwise, maybe we are just a bit late, but I don't think it's a big issue. Yeah, I don't see any other comments, other questions. So last opportunity. Oh, there's Talia. Probably wanted to speak. Yes, please.
Hello.
Hello.
I would like to thank you for giving lovely conversation for us. I would like to make a brainstorming for you, with you. What if I haven't think before what happened in solidification or in heat treatment processes on microgravity environment. But when you say when you started this conversation, I just curious about this. What happened? Diffusional processes, diffusional steps in microgravity environment. What diffusion can affect on this situation? Is there any related information? Do you know? I don't know.
Yeah, it's a great question, Jonathan.
Yeah, I mean, in terms of a lot of these studies where we talk about any type of processing, obviously, your mass transport is governed by diffusion, so it's a heavy diffusion dominant environment. So really, probably the main overarching thought process through a lot of these experiments are let's isolate the diffusive component examine the physics or examine the transport that goes on that's just driven by diffusion to help us understand how does that work, how does that affect if it's a mixing process or a crystallization process. So it's a great way, like you said, to isolate the diffusion component of a system.
Yeah, because every treatment is coming from the diffusion actually, because when you're making heat treatment, you have to look forward to the chemical potentials of the elements in each others. Because of that, diffusion is very impressive acting role on this situation. I didn't think before, but I will search it then. Thank you.
Great. Yep.
Good. So if you want to have some closing comments, otherwise, I think we can leave the people go.
Yes, I think I want to thank everybody. Just a very quick reiteration about like the keep us in mind, because there's a great opportunity right here from a space point of view, and we want to really get to the bottom of what those opportunities would look like for a terrestrial application. So if it comes later, please contact us. Any kind of questions like the one the gentleman just had, any kind of comment, we're welcome. We really want to hear them, and with the EPMA, we'll follow up everything we receive. So that's just my invitation. Please keep us in mind.
Good.
I'll just thanks to you, Bruno, for organizing this. Thanks to everyone around the world for attending this, and we'll get you those slides out. You can use obviously our starting list as a brainstorming list when you have time for yourself to think about, hey, what's relevant. And as Jose mentioned, feel free to contact any of us. We're happy to talk to you further.
Right. We will distribute the slides for everyone. Yeah. So, don't know if you want to say something, Cincy, as well, but
no, for once I
it's
can
done.
keep my mouth shut and just say thank you. Thank you.
No, thank you for being here. I think it was interesting. I think, Kenan, we may even disclose as little secret that we have. We are thinking of organizing also a seminar on aerospace with a substantial part on space as well. So we're working on it. So maybe in the next months we might have some news, and if someone is willing to give presentations, they can just contact us. Okay. You're muted, Kenan.
I'm sorry.
Start again.
Yeah, that's a part of our new structure, especially for the Congress. You know, our classical sectoral groups of hard materials, additive manufacturing, etc., are now replaced by application-based groups, and aerospace is one of them. So why not? We are taking seriously on organizing a kind of conference or seminar on aerospace. So we would like to welcome you for that.
Everyone will be invited. So thanks again for being here. I see someone already left. Of course, it's late. Thanks to our colleagues in the US, and thanks for the opportunity. Thanks to everyone for attending. And if you have ideas, please contact us all. Thank you.
Bye, everyone.
Bye. Bye-bye. Have a nice day. Bye.
Thank you, Kenan. Thank you, Bruno. Ciao.
Ciao.
Bye-bye.